We're very happy to have with us today Jason Liao, an alum of the Johns Hopkins Biostatistics Department and currently a professor at Penn State. So Jason, please feel free to begin.
Okay, thank you, Brian, for this opportunity to present this work. So what I'm going to present is the variance reduction in the inverse probability weighted estimators for the average treatment effect using the propensity score. So this work we presented, I'm going to present is to try to provide a solution to a long-standing problem. That's the variance over the inverse probability weighted estimators are pretty substantial. So we used the Rao Blackwellization idea and come up with a method to substantially reduce the variation of these estimators. So this is a joint work with Dr. Rodi, and I thank him for bringing this topic to me. And so I know you are all very familiar with the Rubin's potential outcome framework and all the basic stuff, but I'm still going just to start with it, just to make sure we are on the same page with the same notation. So we have a treatment variable z. So it's a binary treatment variable, the two treatment groups. So the purpose is to compare treatment z equals 1 against treatment z equals 0. So we have two treatment groups. So we are going to assume the target population Q has the big N subjects. And the outcome variable is called y. So the Rubin's potential outcome theory says the outcome has two potential values. So for subject I, so if the subject I receives treatment 1, then you have the value yi1. And if the subject receives treatment 0, then we have a value yi0. So these two values under different treatment conditions. So theoretically, if we average all these yi1 over all the subjects in the target population, so we get this mu1. And if we add this average all these yi0, so we get a mu0. So this mu1, it's the average of y if all the subjects receive treatment 1. So this is mu0 if all the subjects receive treatment 0. So then the difference between mu1 and mu0, it's called the average treatment effect, ATE. So we're going to call this delta true, okay, delta true. So the fundamental difficulty in this setup in practice is we only observe for each subject either just yi1 or yi0. So we don't observe both of them. So we either observe this value yi1 or we observe this yi0. So we don't observe both. Okay, so that's the fundamental difficulty. So now let's just, we look at the propensity score model. So the propensity score model just says subject I, so each subject has a propensity score and EI. So this EI, it's a function of these predictors. So we call the XI. And so these propensity score is determined by these vector predictors. And then the treatment assignment, it's a random Bernoulli trial. So you just have the ZI has treat value 1 with the probability EI. So has a probability 1 minus Z1 for getting treatment 0. So then if we get a treatment ZI equals 1, then we observe YI equals YI1. If treatment assignment is ZI 0, then we observe YI 0. So that's basic setup. So we want to use this data. So this is the data to estimate the actual treatment effect. Of course, in the real application, this is EI are unknown, but we're going to assume it's known initially, okay? And then we're going to estimate that from the data. So some theoretical insights that helped me. So if we have all these individual propensity scores are the same, then the design turns into the usual randomized trial. So then the analysis is straightforward. So, but what happens if EI differs from subject to subject? So then we can think about, we have many, many local randomized trials. So each unique value of EI will define a subpopulation. So within that subpopulation, you have a local randomized trial. I think this is a good way to look at the things. Okay, so now we're assuming that EI, they're not the same. Okay, so they differ from subject to subject. So what's the consequence of different EI for different subjects? So the consequence is just the imbalance of these predictors between the ZI1 treatment group and the ZI0 treatment group. So we have the imbalance of these confounders between the two treatment groups. So as a statistician, we all know that we can use regression to adjust the imbalance. But of course, that has its limitation, although it's very useful, but it has its limitation. So now in the survey sampling literature, so this imbalance is interpreted as oversampling of YI1 for subjects with a larger EI, and oversampling of YI0 for other subjects with a larger 1 minus EI. So this leads to the inverse probability weighted estimate, so which tries to restore the balance through weighting. Okay, so now I'm just going to talk about the 4 inverse probability weighted estimators we're going to deal with in this talk. So they're from this Lunceford and Davidian, this 2004 paper, which I found it's truly wonderful, amazing paper. In fact, I learned 90% of my stuff about propensity score from this paper. Okay, so here we have 3 inverse weighted probability estimators. So this is 1. So this is the definition. And then we have a delta IPW2. So this is like more smooth version of this one, try to balance out so it balanced by dividing over this value instead of just n. So then we also have this delta IP3, it's more complicated, okay? So now if we look at this, and these estimators will become unstable when EI is close to 0, or when 1 minus EI is close to 0.2, or EI close to 1 for this term. So this is the same for all the inverted weighted estimators. So now let's look at another one. So it's called augmented IPW, or double robust estimate. So this double robust estimate combines weighting and regression adjustment in a single formula. So here we have this weights, and but here we also have a regression estimator of the outcome variable directly. So it combines the weighting and the direct regression modeling of the outcome variable. So the benefit of this one, it's called a double robust. The idea is if you get one part right, and then you're going to get a consistent estimate. So if you get the weighting part right, or if you get the regression modeling of the outcome part right, so then you're going to get a consistent estimate. So because all these four estimators are special cases of a general estimating equation. So it can be shown that the symptotic variance of this IPW1 is largest, and then the second largest IPW2, then IPW3 is double robust one. So if the models are correctly specified, in fact, has the best performance. Okay, so at this time, we're still operating on the true propensity score, EI. Okay, so just if you have questions. So we know that the IPW estimators are unstable. So what are the solutions proposed? So one way, it's called a weight trimming. So this is, for example, in the Li 2011. So the idea is just to replace propensity scores too close to 0 or 1 by values less. So you just replace these two extreme propensity scores by values less extreme. So the problem with this is just ad hoc. So you may have some convenient value to trim, but then it's just they're ad hoc methods. So another approach is subpopulation analysis. And so one way is just to discard subjects whose propensity scores are too close to 0 or 1. Yeah, so the problem with this is one, it's ad hoc, another it's altered population. So you're no longer estimating the treatment effect on the original population. So you have an altered subpopulation. And then we have this paper, Li, and this is a JASA paper, which is in fact pretty interesting. So it proposes a subpopulation. So this subpopulation, it's in fact well defined. So they define that by a so-called overlap weight. And they show that if you estimate the treatment effect in this well-defined subpopulation, then the variance, in fact, is the smallest, which I did a simulation, and that's true. So if you are willing to accept their subpopulation, and then you can really get a very precise estimate of the treatment effect in that specific subpopulation. But the problem is just we have altered population. Okay, so if I'm not clear, just stop me and ask questions. So okay. So now here we're going to transition to the method we are proposing. So in order to that, I'm just going to focus on the IPW1 because all others will be the same. So the first thing we need to do is just to reformulate the estimate a little. It's totally equivalent, just rewrite in a way that will make sense. So this is original formula for this IPW estimate 1. So when you have this ZI equals 1 and you add them up, and if ZI equals 0, so then this term disappears. So this is the same. This is ZI equals 1. Then you have this term, ZI equals ZI equals 0. You have this term, ZI equals 1. You don't have this term. So then we can just write that into this form. So we only need to sum over this ZI equals 1. So this part, and this part, it's only ZI equals 0. Okay, so first, and then we're just going to let M1 to be the sum of all this Z1, Z2, and Zn. So M1 will be its number of subjects allocated to treatment 1. So M1 is just the total number of subjects allocated to treatment 1. And N0 with the total number of subjects allocated to treatment 0. Okay, so we get that one. So then we're going to do the order statistic of this propensity score. So since we have N1 subjects in treatment 1, so if we get all these corresponding EI, so we have N1 of this EI. So we're going to put them into order statistics. So this is in fact very important for what we're going to do. So then we're going to put E1, the first order statistic, and E1, the second order statistic, and then En1, so this is N1's order statistic. This all for this treatment 1 group. And in treatment 2 group, and then we also have this order statistic, okay? So then we define the weights. So weights in terms of order statistic. And so this is the weight for the treatment 0 group in terms of order statistic. So then we can write down this formula in terms of this order statistic. So these are the order statistic. So this is the ordered weights. And these are just this YI, we just reorder them so that they will correspond to the same weights or the same propensity score. Okay, so now you may ask, so why do we have to use order statistic? So what benefit does this bring? So the benefit, so why order statistic? So this is just repeat of what we did. So we have, we get this order statistic. So why do we want to formulate in terms of order statistic? The reason is this order statistic. So this EI1 and this EI, I think I'm getting this is, it's not right. Okay, so this is should be 1I, okay? So this is the 1I. So this means it's the order statistic, I's order statistic for the treatment 1 group. So these order statistics, in fact, will converge uniformly over I. Okay, so we have this one. So this is similar to this very famous theorem in probability. So this Glivenko-Cantillon theorem. So that says the sample order statistics converge to the corresponding population quantized uniform. Okay, so now we get this order statistic. So this originally these propensity scores are random, but if you do the order statistics, then in fact they will have pattern. They will converge to fixed quantity. So that will be useful. Okay, so now we're going to reformulate the whole propensity score sampling plan in a way that will help us to remove some of the variation in the total variation. So this one will tell us when you have a estimator and how much variation do you have? Okay, so we're going to decompose the whole variation to 4 parts. So the first part is if you draw a sample of n subjects, so then you get this EI. So you have E1, E2, and EN. So this is just from the underlying density of this propensity score. So here we get the first layer of variation. So you have n subjects, and then you have E1, E2, and EN. So from one n subjects to another n subjects, and these n propensity scores will differ from one draw to another draw. So this is the first layer of variation. Second variation is we're going to draw N1 as the sum of Z1 plus Z2 and Zn. So where each Zi is just the Bernoulli tribe. So in the step 2, we're just going to decide how many total subjects are allocated to group 1 and how many total subjects are allocated to group 0. So this is another variation. So now, given the first 2 steps, and then we're going to draw this E1 and E2 and EN, okay? So we'll condition on the total number of N1, the number of subjects in group 1. So step 2 generates the total number of subjects in group 1. So then step 3 will just decide which n subjects will be in group 1. So, and then which n0 subjects will be in group 0. So this is step 3. So now step 4, after you generate this individual Zi1, so all these I from this one, so then you can draw this outcome variable Y. Okay, so here we got the 4 components of the total variation. So now we're just going to remove the variation in step 3. So let's see how we can do that. So now so this one, it's a little bit heavy, but cannot make it simpler. So just bear with me a little bit, okay? So we said step 2, it's we generated the total number of subjects in group 1. And N0 is the total number of subjects in group, this is total subjects in group 1. This N0 is the total number of subjects in group 0, okay? So then in step 3, we're just going to decide which of the N1 subjects will be in group 1 and which N0 subjects will be in group 0. So in fact, this is a number of possible choices. So it's N choose N1, so it's a huge number of choices. So now, if every consequence of this Z1, Z2, and Zn, so if you have a sequence of Z1, Z2, and Zn, so that's a potential treatment assignment. Okay, so there is N choose N1 of them, so it's a huge number. So each this sequence will lead to a unique order statistic for treatment 1 group and this unique order statistic in the treatment 0 group. So then it will lead to a unique IPW estimate. Okay, so now we see this step 3, there seems to be a large variation in it because you just have so many potential treatment assignment So this n choose n1 of them. So each assignment will lead to a unique estimate. Okay, so this is a huge variation in this procedure.
Jason,
So now,
can I ask a question about this?
yes.
So when you run the Bernoulli trials for each E, that is not actually assigning the subject for whom that is their propensity score to either treatment or control. I guess I'm confused about the fact that the assignment of subjects to treatment group is done by first flipping a Bernoulli coin conditional on the individual's propensity score, and then ignoring the result of that and looking at the n choose n1 possible assignments, which I see do depend on those propensity scores again, but it seems.
Yeah. So the usual way, so let me know if my understanding of the usual way is correct. The usual way is you just do this one, right? Do this EI, this Bernoulli trial for EI. And for I equals 1 to n. So then you are going to determine a sequence of this ZI. So that will be a sign of treatment assignment, treatment allocation. Is that right?
Yes.
So that's the usual way. So this way can be decomposed into step 2 and 3. So the reason I have to decompose in 2 ways. So these are the step 2 and step 3 and the usual ways. Just one sequence of n Bernoulli trials are statistically equivalent. So the reason I have to write them into this way, it's because I cannot remove the variation in n1. Yeah, and cannot remove the variation in n0. But conditional on this n1 and n0, so then I can remove this conditional variation. But mathematically, they're equivalent. So if you just get these 2 steps, and it's the same as you just generate this n Bernoulli trials to get a treatment allocation.
Okay. I don't see how it's equivalent, but I guess I can see that it could be, and I'll just have to think about it more.
Yeah. So this one, so you just do the conditional. So you get this n1 and n0 as a marginal, and you generate them first, and then you condition on this marginal, then you get the rest of this the assignment. That's at step 3. So I do have this conditional distribution written out explicitly in the paper. So
I guess what I don't, yeah, okay, I'll look into it. The part that I'm confused about is I see how you could do step 3 conditional on n1 and n0. I don't understand the generating n1 and n0 from the Bernoullis, but then ignoring those Bernoullis. But I guess actually now that I'm talking through it, I see how you're getting the induced distribution, probability distribution on n1 and n0. It doesn't matter. The fact that you get that from the Bernoullis is just me ensuring that it's correct relative to what you are assuming about the data. But okay, sorry,
yeah.
I'm taking up too much time, but I get it.
Oh,
now.
no. So this n1, in fact, it's the Poisson-Bernoulli trial binomial. I think this is if you can do this n1 as the Poisson binomial, I think that's its distribution. So you generate this, then you generate. Yeah. So they're indeed equivalent.
Got it. Okay, that makes sense. Thank you.
Okay, thank you. And so after we get this, each sequence of Z1, Z2, and Zn will lead to a unique IPW estimator, so this form. So now this one contains a huge variation. Just look at this, you have so many of the possible choices. So now the smooth estimator, the idea is very simple. So instead of using this WI1 and the WI0, you just use the expectation. So you just get its mean. So you replace these weights, original weights, by their mean. So this average is over all these n over n1 potential treatment assignments. Okay, so one thing I need to just mention is I usually try to hide it, but so now I think so although I say it's over all these potential treatment assignments, so it's over their distribution. It's not just arithmetically. So you just get all these n over n1 potential assignments and then just do the average. In fact, each of these potential assignment has a probability. So we're going to average over the probability of that distribution. So now the smooth estimating equation, it's very similar. So all we need to do is replace this original weights by the average. So this is the average. We get the average. So okay. So now let's see. So what's the big difference? The big difference is the original. So if we already have Z1, E1, E2, and En of these n propensity scores drawn in step 1. And the original estimator, so this estimator, in fact, the estimator depend on this unique treatment assignment. So depend on this Z1, Z2, and Zn, so this sequence. But if we use this weighted estimate, it no longer depends on this the sequence. Okay, so this a particular assignment of Z1, Z2, and Zn doesn't matter because we're averaging over all these potential assignments. So instead of we have a unique weight for each of this treatment assignment, we're going to average over all these potential treatment assignments and get a unique, get this value. So the variation is substantially reduced. So before we have the variation that depends on what unique sequence of Z1, Z2, and Zn. So now we just average over all these potential treatment assignments. So we get rid of this huge variation in that one. Okay, so now at this moment, you may think, am I going wild? So how can you just do you just average over whatever you want to average? Well, in fact, it's not just some wide guess. In fact, it's based on this Rao Blackwellization. Okay, so
Dr. Liao, may I ask a question here?
Yes, yeah.
Isn't YI bracket 1 changing as well, given each Z1 to Zn? Is it fixed?
Yes,
so,
yes.
So how
yes.
do you, what will be your YI1 when you replace WI by WI bar?
Yeah. So glad you asked that question. So I'm not going to change that one. And so in a moment, you're going to see what's going on. Yeah. So I'm only going to average over this weights. I'm not going to deal with this Y. So they were still the same. So they still stay there according to original order statistic.
Thank you.
Yeah, but great question. I think you see everything, what's going on. Okay, so now let's see. So what's the idea? So this Rao Blackwellization. So this original theorem says if you have this phi x, it's an estimate of a parameter theta, and the Sx is a sufficient statistic, and then you can average on the conditional distribution on Sx. So if you do this one, So then you're going to always improve the estimate. So the mean of this by average over this estimate, conditional on a sufficient statistic. So you're always going to have the same mean, but a smaller variance. So this is a standard one. So this Cassell and Robert, so they studied the MC and MC, and they found that the original theorem is a little bit restrictive. So what they said, it's easier to apply. They stated that one can interpret the Rao Blackwell theorem as saying that if the calculation of a conditional expectation, so you can just do the conditional expectation, so long as it results in the estimate, then such an estimate is always superior to the original. So you can free to average, so long as the product of the average does not depend on the parameter of interest. So you can.
Before we go on, there's a question that someone wrote in the chat.
Yeah.
Won't the estimating equations be biased if we only adjust the ordered weights?
Yes, it will. So let's say. So yeah, that's true. But what we are trying to do is to introduce a little bit bias and for substantial reduction in the variance. So here it's how we can justify that. So this is the intuition for the smooth estimate. So now we have this, the formulation of this IPW1. So this IPW1, we have this W part, this weight part, and we have the outcome part. Okay, so this is the same thing here. Okay, so the basic idea is these weights are unstable, while this Y, they're stable. Okay, so now so how is that so? So what we showed in the paper is these order statistic, in fact, will uniformly converge to this epsilon. So this epsilon, it's a fixed quantity determined by the distribution of ER. Okay, so this order statistic, so this is order statistic for all the E in the treatment one group. So if you look at all these order statistics, they in fact will converge to fixed quantities uniformly. And this fixed quantity is determined by the distribution of ER. So it's the FE. So this is just the distribution of all these propensity scores in the population. So it's determined by that. So it's not random. So that's the key insight. Okay, so now we know this order statistic of the propensity score, in fact, will converge uniformly. So now we look at this outcome variable. So this outcome variable is drawn from this distribution. Okay, so this yi1 is drawn from this distribution. So if this distribution, so this is outcome variable, distribution conditional on the propensity score, given the propensity score. So if the mean and the variance of this outcome distribution has a bounded first derivative, so then the mean of this will also converge uniformly. Okay, so I think this is a safe assumption that the mean and variance of the outcome variable it's smooth, because we have all these propensity score matching, propensity score stratification. So they are all based on the idea that if two subjects have similar propensity score, has close propensity score, and then their mean and the variance will be, or the distribution will be close. So, okay. So now we said these are all the statistics of the propensity score will converge. This one will lead to the outcome variable. The mean of this outcome variable will also converge under certain conditions. But the weights, they do not converge because the weight is 1 over the propensity score. So you don't have the finite first derivative. So the weights do not converge. So that okay. So am I convincing so far? So,
I
yes.
I have a question and a comment.
Yes.
So the comment is for your second bullet point, you were saying you were justifying why you would think there's a bounded first derivative, but there could be covariates that affect heterogeneity in the outcome that are not confounders. Would that be a problem for your rationale?
Yeah, but I thought the propensity score, you can ignore the predictors when you have the propensity score, right? So you don't have to worry about the predictors.
Yeah, that's true. But just in terms of, if I caught what you were saying, right, it's that conditional on the propensity score, the distribution of y should be not too variable.
Yeah.
And the counterexample that I can think of is if there's a really strong predictor of y and of treatment effect or outcome heterogeneity that is not a confounder, then it's not included in the propensity score. And then I wonder if you would get lots of residual differences in the distribution of y, even conditional on the propensity score.
Yeah, I think what you said is right, but I'm counting on in the most cases, and this one will be a smooth distribution over the propensity score. So when the propensity score changes a little, and then the distribution of this y will not change too much.
Yeah,
So,
that does sound reasonable. I agree.
Yeah, and as a contrast, and the weights are totally different. So the weights, because when the weights this gets close to 0 or 1, so then they just behave widely. So
yeah. So my second question was, a lot of times people will make the strong overlap assumption that the true propensity scores are bounded away from 0 and 1.
Yeah.
And does that get around this issue?
No. So that only gets around the issue theoretically, okay, not numerically. So
yeah.
For example, if it's bounded away from 0, so how close from 0 it's bounded away from 0? This is not mathematics. You bound away from 0 for any small number. So in practice, if you're bounded away but still close to 0, so then you're still running into trouble. May not be the biggest trouble. You still,
yeah. Thank you.
Okay, thank you. These are great questions. Okay. So then the proposed smooth estimator, it's the Rao Blackwellization. So if you are willing to replace this y from this distribution by yi under this limiting distribution. So remember this epsilon, this I, this one, it's a limit of this one, right? So this will converge to this uniformly. So if we are willing to replace yi from this distribution to yi from its limiting distribution, So that's all we need to do. So if we are willing to change that distribution to this distribution, then the smooth estimate, in fact, it's exact the Rao Blackwellization. So we basically change one part of the process by its limiting process, and then we get the Rao Blackwellization. Okay, so the idea is by introducing hopefully a small bias, okay, we are aiming for a much big variance reduction. So because this thing is really where the trouble comes, this weights, and so good. So now, so far we've been assuming that we know the propensity score, but in fact we do not know it. So then in the practice, so you just replace that by the estimates, okay? So this tries to show that even if you do the estimates and then you just estimate, so original propensity score, it depends totally on these individual estimates of the propensity score. But if we use this weighted or smoothed propensity score, and then it only depends on their mean. So if you have a sequence of these estimates, and they have the same N1 and N0, so this weighted estimated weights will be the same. So it provides a much stable target to estimate. So instead of you have to estimate individual, this one, so now you basically have a much stable target, which is the average. So now, wow, so time it's getting fast. So we did a pretty comprehensive simulation study. So I think the time is running a bit short. So I'm just going to present some of the major result. So this one is IPW1 original. So this is a 500 samples, and that's estimation error. So this is the smoothed one. So all these big errors are smoothed out. So this is IPW2. So then we have also, it's better, but still very variable. So this is a smoothed one. So this is IPW3, and this is smoothed one. So we see a substantial variance reduction, especially for these first two. So we get that one. So now we have this number result. So here we get, so this is IPW1, this is the smoothed one. So this is the mean of the bias. So this is the bias, and that's the variance, or the standard deviation. So so we see a substantial, this is about 3 times reduction. So here it's IPW2, also a huge reduction. So this IPW3. So here it's a more interesting one. It's about this double robust. So these double robust one, so here we have some misspecification of the outcome variable y. So it's a regression model for the outcome variable y. So we introduce some misspecification for the model and see what happens. So this, then this original double robust, the standard deviation of the error, 0.173. So robust becomes 0.158. So here we get a more severe misspecification of the outcome model. So the standard deviation from 0.216 reduced to 0.16 something. So it does provide substantial protection against misspecification of the outcome variable for this double robust estimate. So the summary of the simulation study is just a substantial reduction for IPW1, IPW2, and IPW3. So for the double robust estimator, so if all the models are correctly specified and the smoothed version does not seem to help, but if the outcome variable model is misspecified, then this smoothed version can noticeably improve the double robust estimate. So which makes sense because the double robust estimate depends on two parts to make the right. So the smoothed one so strengthens the weighted part. So I think another interesting thing is you look at these IPW1, IPW2, IPW3. So originally they have really different variation, but after smoothing, so they all become almost the same. So seems the smoothing just goes much further than these IPW2 and IPW3. So originally you have smoothing from IPW1 to 2, and then further smoothing, stabilization to 3. So now if you use our smoothing, then they all become the same basically. Yep. So, and so here it's an independent study. So it's by a Japanese researcher. I copied it from his slide on the internet. So he added the comparison to this paper, IMA and Rotkovic. It's the 2014 JISSB paper. So he included this for comparison. So this is their method. And so this too is a true value. So this method does reduce the variation considerably, but unfortunately, we observe a pretty substantial bias here. So this is our proposed method. So we have a lower variation, but in fact, very little bias. And so we also have a non-parametric bootstrap method and to do the confidence interval. So here it's one example. So it's real data. So it's Ohio heart study of 996 patients. So the outcome is a cardiac related cost. And the two groups and the predictors, 7 predictors. So here it's very telling is if you do the raw IPW1, IPW2, and IPW3, so then the IPW1 is in fact negative, and these IPW2 and 3, they are very close. So if you use the smoothed version, all the 3 are basically the same. So the smooth does make a difference. So, and more importantly, so if you have the smoothed IPW1, the confidence interval is pretty narrow. So the original one, the confidence interval is very wide. So this is a huge difference between the two methods. Okay, so if we want to try out, so I have put the R function. So it's very easy to use. So if you go to my website, you can find an R function called smoothed P scores. So all you need to do is to put your original propensity score and the corresponding treatment assignment. So then it will output the smoothed propensity score. So then you can use the smoothed propensity score in place of your original score to do whatever analysis you want to do. So I feel confident that you're going to benefit from this one. Okay, so the summary of the talk is we proposed a smoothed version of the popular IPW estimators. So substantial variance reduction. And for this robust estimator, double robust estimator, we provide added protection against misspecification in the regression outcome model. So thank you very much for your attention. So please ask any questions. Yep.
Thank you very much.
Oh, thank you.
That was great. Anyone want to start off with a question? I think Michael?
Yeah, first I wanted to thank you for the excellent presentation. It's very impressive what you've done. I love it. I really love it. Yeah, it's a great insight with applying the Rao Blackwellization that way. And that I wanted to ask if your smoothing approach, does that impact the asymptotic variance at all? Or is it, I know it improves things in finite sample, which is arguably even more important, but is there any impact on the asymptotic distribution?
Yeah, definitely. I try to look at the asymptotics, but it seems it's too hard. So then I just develop a non-parametric bootstrap. So I don't know, but I think it will be a substantial undertaking to figure that out.
Okay, great.
Yeah.
Thank you. Yeah,
Yeah.
Interesting. Super interesting.
Do you have an intuition about that? Mine, I wouldn't trust as much as yours, but mine would be that it would affect asymptotics except in the doubly robust case.
Yeah, I think the double robust case, even in finite sample, if your both models, the propensity model and the outcome model, are correctly specified, the smoothness does not really help. It's the same thing. So your intuition, I think it's right on, I think.
And
Yeah.
I was going to ask for the doubly robust case, a lot of the work around these doubly robust estimators these days is on using fast machine learning models for the nuisance parameters. Does any of your theory break down if you're estimating the Oh, okay.
So this is a slide I added. So what happens when the propensity scores are estimated from the data, right? So I do not have much knowledge about machine learning, but after the talk at the Penn, I did look at a few papers. So my understanding is the machine learning is just a very parametric approach to estimating this propensity score that impose less modeling. Am I right on this one?
You said it is parametric?
It's non-parametric.
Yeah, that's exactly right. Yeah.
So if we use the non-parametric, so the benefit is you get less bias. So, but you cannot avoid the increased variance compared to the parametric method. I think no one can get around that. So you cannot, in that method, that's just good in both reducing the bias and reduce the variation, because they're conflicting aims. So if that's true, so then the non-parametric one, they will get these estimated propensity scores with a larger variation. So I think that has to be right? So if you can have a correctly specified parametric model versus a non-parametric model like machine learning, so the machine learning will have estimate of these propensity scores with a large variation. Okay, so if you have large variation and you plug into these IPW estimators, so these variation will have to carry on in these estimators. Although there is a special case. It's a little bit over smoothing, a little bit overfitting in propensity score. It's in fact beneficial. That I know that part. But if you overly non-parametric, overly flexible, and then the increased variation in propensity score will have to impact the IPW estimate. So am I right on this statement?
Yes.
Okay. So then in that case, I think my smoothing will be even more beneficial because that will in fact smooth out some of the variation in this estimated propensity score. So I'm not convinced like the Eric, like at Penn. He seems to think that machine learning that will solve all the problems. So but I do not know too much about machine learning, but that's what I think now.
Great. Yeah, so I guess my concern was that, I don't know, maybe the convergence of, well, yeah, no, I guess short of asymptotic results, there's not much to be concerned about. But yeah, I think to me, what's most powerful about your results are that they don't undermine the doubly robust estimator, but they have the potential to improve upon it. So it seems like, even if, I guess my question was, doubly robust estimators are used in two ways. One is to get this double robustness, and one is to allow you to use machine learning, non-parametric models for the regression and propensity score models. And it sounds like you're saying that you suspect that the advantages will carry through and possibly even be stronger in that latter case.
Yeah, so the double robust estimator depends on the two parts to work. It's called magic. So one is the weighted part has to be good, right? So then the regression of outcome needs to be good. So this smooth estimator will strengthen the first part. So if you get the second part not right, because we have the first part, it's better. So that will improve it. That's what I think.
Dr. Liao, do you have time for one more question?
Sure.
Okay, so this was in the chat from Ravi. I was going to ask something similar. When we say that the increased bias is small,
yeah,
compared to the variance decrease,
yeah,
to what extent are you confident that that's true for all cases, or are there some conditions that guarantee that? For example, like whether the effect is heterogeneous or not?
Yeah, I cannot guarantee, but I do specify the exact the deal you're getting. So what you're getting is, if we are willing to replace Y from this distribution by Y from this distribution, and if you believe that the valuation of this distribution, as it depends on the propensity score, it's less wide than the weights dependence on the propensity score, then you probably will benefit. So I think in majority of the cases, you will benefit. And if this assumption is not reasonable, then how do you do all these propensity score, like the matching and the stratification? So they're all based on this idea. So if the propensity scores are close, then the distribution of the outcome is close. Yeah, so yeah, I cannot guarantee it will work for every problem, but I think it will work probably on majority of the problems.
Okay, that was really interesting. Thank you very much.
Thank you. Yeah.
And thank you everyone for coming. We'll be meeting again in 2 weeks. See you all then.
Okay,
Thank
thank
you so
you.
much,
Bye-bye,
Jason.
everybody. Yep.
I learned
Bye-bye.
even more this time. This was great. Thank you. I really appreciate
Thank
it.
you. Yeah, okay. I will see you.